Okay, very good. So any questions from last lecture so far or before I start? No? All right, so then let's get started. So as I promised, I'm going to do quadric surfaces this time. I guess I'm within the limit. Yes, quadric surfaces. So I wrote down last time the general equation for a quadric surface. It's a second degree equation in x, y, z. It's as general as it gets, right? And the question is to find the set of all points in space, x, y, z, that satisfy that quadric equation, like x2 plus y2 plus z2 equal to 1, or x2 plus y2 plus z2 equal to minus 1, for example. We have to be able to handle as many scenarios as possible. And in each case, we should say what the answer is, what shape and form these answers come, right? So the easiest way to handle this for us is to first give some cases, and then we identify those cases with certain shapes. And then some cases we cannot identify. Some algebras we cannot, algebraic combinations we cannot identify, unfortunately. But that's okay, you'll do that in linear algebra in maybe other courses. But what we learn already is quite valuable. So the first case, so I'm gonna write it like this. We have three pluses. So it's like x2 over a2 plus y2 over b2 plus z2 over c2 equal to 1. So this case is well known perhaps to you. This is called ellipsoid. So this really corresponds to, if you draw this in 3D space, corresponds to an ellipsoid, which is a kind of egg-shaped surface. So here is maybe x-axis, and the other one is y-axis, this one is z-axis. Okay, so with the xy plane, the intersection is an ellipse. With yz plane, I'm not going to draw it here, but the intersection is again going to be another ellipse. And with xz plane, its intersection is also an ellipse. So that's why it's called ellipsoid, because any intersections you get with these three coordinate planes is an ellipse. So it's a kind of three-dimensional version of the ellipse. But remember, this is a surface. It's not a solid object, right? It's a two-dimensional object. It's a surface, okay? So that's one case. Next case is we have two plus and one negative. Let's go case by case. It's going to be like x2 over a2 plus y2 over b2 minus, so I said plus plus minus, z2 over c2 equal to 1. Now, if you look at this case, this is called hyperboloid of one sheet, for a reason that I'm going to explain to you right now. First of all, as far as drawing this is concerned, we can just draw it like this. So this is going to be okay. So maybe I go like this. It's better to actually draw like this. So this is the origin. And this is again like X, O, Y, and this is the axis, right? So, yes, so this is intersections of this with planes z equal to constant or ellipses with different parameters of different eccentricities. So if z is equal to 0 here, so the intersection with z equal to 0, you get this, you put z equal to 0, you get the ellipse x squared over a squared plus y squared over b squared equal to 1 plus z squared over c squared. But I said this is equal to 0, so this is 0, so this is 1. So you get an ellipse x squared over a squared plus y squared over b squared is equal to 1. But as you move z upward, you increase z. You see the right-hand side increases. You're adding to the right-hand side. Right? And if you go down, there is a symmetry. If you change z to minus z, nothing changes. So you get the same ellipse when you cut it with plane z equal to -2 or something, -3 and so on. So it's completely symmetric across these by changing z to minus z. Of course, this shape has a lot of other symmetries. For example, it has rotational symmetry and all these things. But for now, this is that one. So this is hyperboloid of one sheet. One sheet is because it's connected. It's just one surface. It's not doesn't have two pieces, and it's called hyperboloid essentially because hyperbola corresponds to y2 over b2 minus z2 over c2 equal to 1. Things like that. So that's basically the reason for this hyperboloid. So this is the second case. Now the third case could be 1 plus, and then there is 2 negative. Right? So this would be x squared over a squared minus y squared over b squared minus z squared over c squared is equal to 1. Right? Okay. So what kind of surface this corresponds to now? Right? So we have to analyze this case. So if you bring this to the right-hand side, just to get a better feeling, you get x squared over a squared is equal to y squared over b squared plus z squared over c squared plus 1. You notice that this is a non-negative number, right? And you're adding it to 1, so this is always bigger than or equal to 1. So what do you infer from this situation? You infer that x squared over a squared is always bigger than or equal to 1. Can never be less than 1 because of this thing, right? It's positive plus 1. Okay, so it means that absolute value of x over a is always bigger than or equal to 1, right? So it means that either x is bigger than a, assuming or x is less than. Let's assume a is positive. It doesn't matter minus. So this already makes this surface look like it comes in 2 pieces. One piece corresponds to x bigger than or equal to a. The other one is x less than or equal to minus a. Right? So the axis that's relevant here is this axis. So let me draw it like this. So, you know, the trick with drawing these things to some good scale is not to draw the coordinate axis first. Draw the surface by what you know, and then fit the coordinate axis. So you have to cheat a little bit here. Okay, so anyhow, so we have this. Okay, so now the x-axis, I'm gonna put it here. This is the x-axis. And this is y-axis. This is z-axis. So this surface has two sheets. Of course, this x-axis goes down. But now you may complain that, hey, why the x-axis is like this? You always drew z-axis like this one, but then it doesn't matter. You can rotate and then see that, but it's just more comfortable, more convenient to draw it like that. Right? So let me just draw this line so that you know. Okay, so this is, the name then is hyperboloid of two sheets. So this is hyperboloid of two sheets. It comes in two pieces like that. Okay. Oh, there is a question or comment maybe. We should. Can't see the whole drawing. Oh yes. Right. Oh, I went out of board. Sorry about that. So can you see better now? Okay, I'll make sure I won't go out of limits, because here, from here, actually is out of limits, really. It's hard to, no. Okay, so, okay, I'm gonna go back to my original scale. That's tough. Okay, so I have to make sure that I won't go beyond this line. Yeah, sorry about that. Okay. So this is a hyperboloid of two sheets. Now you might say, what if I have 3 minus? That's a reasonable question. What if you have 3 minus? What would be that case? Right? I mean, the 3 minus sign. Can I erase this part? Can I erase this part? What if you just get 3 minus? For example, you get minus x squared over a squared minus y squared over b squared minus z squared over c squared equal to 1. I mean, logically, this is a possibility, right? I mean, in terms of equations, everything goes. So we have to write down the equation and analyze. So what happens in this case? Any answers?
You get a negative ellipsoid.
What is negative ellipsoid?
I don't know if you pull out all the negatives, you just get the equation for an ellipsoid. So an ellipsoid with an inverted radius, however that would look.
Oh, that's a good imagination, I would say. Yeah, that's a good thinking. But okay, so any other answers?
You just get an ellipsoid.
You just get again an ellipsoid because you're saying you can multiply by -1. Yes, there was another. No? Any answer from the audience? What shape corresponds to this one? Minus x squared over s squared, minus y squared over minus z squared over c squared equal to 1. Well, the answer is this is empty set. I mean, there are no solutions. So it corresponds to empty set. No points in a space could satisfy these equations. Well, that's not a problem. This is just empty set. So let me just write it down. In this case, we just get the empty set. So this is a bit of a tricky question, actually, but it's good to know these scenarios, possible scenarios, right? So this case, no solutions, right? So there is no real surface that corresponds to this. So the set of solutions is just empty set. Perhaps you know the notation for empty set like that. Yes?
Is there like no solution whatsoever, or just no solution in the real
Yeah, no solution in the real world, right? But there are some interesting solutions if you go to complex numbers. So for math enthusiasts, I should say, yeah, you will see that this becomes a very interesting object if you go over complex numbers. But in the real world, for us, we have limited vision so far. So this is just, we are confined to real numbers, so there are no solutions. Yeah. Okay. Right. Okay, so that's one case. That's good that we discussed. Now, let's look at some other cases. For example, x2 over a2 plus y2 over b2 equal to z2 over c2. So this case, it looks like similar to that, like 2 positive, 1 negative. But notice that the right-hand side now is completely 0. So it doesn't come, this case doesn't come under this sort of situation. It's just an independent case we have to treat. What kind of object this corresponds to? Yes.
I think a 3D parabola.
A 3D parabola. Good guess, I would say. Yeah. I mean, thank you for guessing. That's very important to commit yourself to answer. But then that's okay. Just that's the way you have to guess and then try and then corrections. I mean, that's the process. Yes. Sphere. Okay. So if we're going to be a sphere, first of all, A and B and C would have been the same, and then this would be plus. Then would be some constant on the right hand side. So this is again, I would say good guess, but it's not in a sphere. Good try. I mean, from home audience, any answers? Okay, no, I mean, I don't. I mean, because this is a bit tricky. So this is called an elliptic cone. This is really a conical object. So this is, huh?
That was my next guess.
Yeah, right. Elliptic cone. So what does this elliptic cone look like? Well, it's really like a cone. It's actually a double cone, so it's really up and down. There is a singularity here. And if you cut it with any plane z equal to constant, you're going to get an ellipse in general. That's why it's called elliptic cone. So this is an ellipse here. There's an ellipse here. There's an ellipse here. And so on, you go down. So of course, this is z-axis, z-axis. This is x, and this is y. So this point is a very special point. It's a singularity at this point, right? There's a singularity. That's okay. Yes?
Are those lines completely straight?
Yeah, these lines are completely straight. Yes, indeed. That's the feature of cone. That's what makes a cone cone. Right, so that's this is exactly. That's a good question. Exactly, they are completely straight. Now, you see, for example, you notice that the point, the origin is on this surface, because if you put x, y, z equal to 0, you have a solution. Right? So at the origin, there is only one point. Of course, origin is only one point, but if you put z equal to 0, you really do get 1 point. As you move z upward, so you change the right-hand side of this equation, and you get the family of ellipses stacked one over the other. So you construct this cone by putting the family of ellipses over each other, going up, and then also going down. But now you might say, but why this is a straight line? That's a fair question, because in cases like hyperboloid of 2 sheets, we also had kind of like ellipses or circles stacked one over each other, but they moved up in a curvy way, not in the line way. Why we get a line here? The reason for that is that if you put x, for example, equal to 0 or y is 0, so put x equal to 0, you want to see, for example, the intersection? If you put x equal to 0, you do get y squared over b squared equal to z squared over c squared. And this means no more, no less than y over b is equal to plus minus z over c, right? And these are equations of lines. So similarly, if you intersect it with any plane, which is orthogonal to xy plane, it's going to intersect it in a line. So it means that all these planar intersections are actually a line. So it's actually ruled by a kind of line moving. Right? So we pay attention to this cone. I mean, that's what is the feature of cone? There are no constant terms, two positive, one negative. Of course, I mean, you can write it in the other side, and then you do get a cone, but with axis rotated, right? So that's quite possible to get such cone. Okay, so we have this elliptic cone. Now, okay, so cases that we discussed so far, can you tell me what was the kind of maybe general feature of these cases? One general feature of every case that we discussed so far, what was it? Well, the case was that they are quadratic, right, in x, y, z, and at most there was one constant or there was no constant here. But they were all second degree, right? We just had second degree. Or maybe complex numbers, yeah, it doesn't work, that doesn't exist in our. Also, there's also some discussion among the audience, so that's which I'm not supposed to participate. I guess that's okay. Okay. So anyhow, but now I said that any second degree equation in x, y, z. So there could be some first degree term, for example, in x, because the equation I wrote last time, there were cases like ax plus by plus cz plus d also contained in that equation, right? So then let's look at the case where there is some constant, first degree term. So the next case is z equal to x2 over a2 minus y2 over b2. So yes, so the question is that, well, we have this equation, right? Z equal to x2 over a2 minus y2. What kind of shape it corresponds to, right? Again, the way to understand the kind of shapes is to take z equal to constant and start moving z upward or downward. So in other words, intersecting your surface with plane z equal to constant, and then see what kind of curves we get. And those curves are stacked on top of each other. As they move, it gives you a kind of idea of profile of the surface. That's the way, one way to approach it. Okay. So what do you get if you get z equal to 0? If you put z equal to 0?
They're eating Pringles. Pringle chips.
Pringles.
Like one of those.
Yeah. Yes. Exactly. That's absolutely correct. But that's the final answer.
Yeah.
I want to move and in a slow way, slowly, so that to reach to your answer. Yes. So what if we just put z equal to 0? Well, if you put z equal to 0, what do you get? Yes.
X squared over a squared equals y squared.
Which is?
Which is like x over a plus minus y over b.
Right. So exactly. So let's put z equal to 0. And so in other words, we are just studying what kind of trace this surface has, what kind of intersection with the xy plane, right? So put z equal to 0, we get x squared over a squared minus y squared over b squared equal to 0, then what do we get? What kind of curve in xy plane this corresponds to? Yes.
A line.
One line?
Two
Or
lines.
2 lines, yes, exactly. This you can write it as x over a minus y over b times x over a plus y over b equal to 0. So it's a pair of lines, x over a equal to plus minus y over b. So the xy intersection, z equal to 0, there are 2 lines. That's it. So this surface, when it comes to the plane, it just intersects on 2 lines. But maybe that doesn't give us much, right? We have to still analyze what happens if z goes up and z goes down. So if you put all this, so I mean, you get hyperbolas, right? But for z different from 0, we get a different hyperbola. In any case, so when you put together all those hyperbolas for z positive, z negative, you're going to get a shape, a surface, which is indeed like a Prego or a horse saddle. That's, or a kind of a mountain pass. When you're moving up the mountain from one direction, you're moving up, from other direction, you're going down. This is always, mountain passes always look like that. Right? So let me draw that. Yeah, I mean, there are different designations. My students always prefer Pringles. So. At first, I didn't know what Pringles are. So. I had to be explained. And then next lecture, one student brought me some Pringles. Okay, so anyhow, so this is really, so I'm going to, okay, so I mean, I'm more inclined toward drawing it like a saddle rather than Pringles. So, but yeah, I should have brought some Pringles. Anyhow, you have some? Unfortunately. Okay, good. So now, yeah, so what is this? This is the z-axis. This is origin, and this is x, and the other one is y, for example. So notice that if we move up, if you go in this direction, in one direction, you're moving up, and in this direction, you're going down. So this point is neither a maximum nor a minimum. So this is a saddle point, right? So this point is a saddle. That's important. It's a very important concept, the concept of saddle, as we'll see. Is a saddle point. Neither a maximum nor a minimum. It's neither of those. But you notice that it's not a generic point either. It's a very special point, this saddle point. Something very, very interesting is happening at this point. And in fact, what happens is that this is a critical point for this surface. All partial derivatives of 0, and we will study this kind of situation. So this is called what is the name of this? This is called hyperbolic paraboloid. So sorry about this. This was not invented by me. So it's called hyperbolic. Yeah. I believe, yeah, this is called hyperbolic paraboloid. I have to check myself. Yes. That's this case. Now, the next case you might wonder is what z is equal to sums of 2 squares. That's also a possibility. We didn't discuss that. So z equal to x squared over a squared plus y squared over b squared. And you notice that here you're dealing with ellipses. So you're dealing with families of ellipses. So this is called the elliptic paraboloid. Now, as far as drawing this goes, so again, we analyze it by giving different values of z. If z is equal to 0, what kind of point this corresponds to? If z is equal to 0, then x and y have to be 0, right? Because sums of two squares cannot be 0 unless all of them are 0. Okay, so if you allow me to raise this, by the way, this is my favorite surface. This is my favorite. Not that I like horseback riding, but this is really, saddle is a very, 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 very important kind of surface. So let me just draw this. Okay, so here, and you notice that z cannot be negative because it's sums of two squares, right? So you cannot go below this xy plane. This is always above the xy plane, right? This is always above xy, this one. Okay, so, and then when z moves, you get families of ellipses parameterized by this parameter z. Okay, so then this is kind of clear what it is. So this is an ellipse. So this is your x, y, and this is z. As I said, you cut it with each z equal to constant, you're going to get an ellipse. In the plane z equal to constant. Now, the idea that we call it elliptic, it's kind of makes sense, right? Because it's x2 over a2 plus y2 over b2. It's an ellipse. Why is it called paraboloid? Yes.
Because the sort of outer boundaries of the ellipses increase parabolic.
Yeah, I think that's the reason. In terms of equations themselves, what was the equation of a parabola? It was a second degree term equal to first degree term, right? You remember a parabola was like y equal to x2, first degree term, second degree term. And exactly that's what's happening here. A first degree term is equal to, if you put this y, for example, something maybe 0, you get first degree term equal to second degree term. So this is the source of this terminology. Again, so we have paraboloid here. Also, why again paraboloid? Because this is the first degree term. Why hyperbolic? Well, it's hyperbolic because hyperbolas are x2 over a2 minus y2 over b2. You remember hyperbolas from, I don't know, high school or things like that, I've seen. So this is like one example. I mean, I can draw it. Can you give me a rough equation, kind of equation for this curve I have drawn here? What kind of hyperbola is that? Give me an equation for this curve. I mean, I have to be more careful, so what kind of surface, what kind of curve, what kind of equation corresponds to this curve? You know there are two cases, right? Either x2 minus y2 equal to 1 or y2 minus x2 equal to 1. Either of these two cases, because these are the hyperbolas that you learned in high school and also calculus 1000 or something like that. So is it this one or that one? Is it this or that that corresponds to this? This or that? Audience? First one, yes. I got an answer, okay, from Nabil. Yes, first one. Yes, indeed, this is correct. Thank you. Yeah, very good. Indeed. You see, this cannot be corresponding to this, because if you put x equal to 0, for example, in this case, or maybe, I mean, this, if you put y equal to 0, there are no solutions. But here, y equal to 0, there are two solutions. For example, plus a minus a, or plus 1 minus 1. So plus minus 1. So this cannot be the case. So this is the case. And you see that if you put y equal to 0, the x-intercept is 1 and minus 1. As you move up, you get this one. Right? So that's a kind of important thing to bear in mind. Yeah, okay, so I've got this. Okay. Okay, so we have got this elliptic paraboloid, hyperbolic paraboloid. So this is the, we have two in the paraboloid family. And now, we can do variations on this, right? For example, I mean, you can do some cosmetic changes here. So let me tell you what I mean. So let me put it like this. Note. Can you read that? Yeah. Okay. Note. In all above cases, can replace x by x minus x0, y by y minus y0, z by z minus z0, and then we get equations like x minus x0 squared over a2 plus y minus y0 squared over b2 plus z minus z0 squared over c2 equal to 1, right? Now, this is also an ellipsoid, but its center has moved to point x0, y0, z0. It's again an ellipsoid. Just no more, no less than an ellipsoid. Okay. With center, where its center is at, center at x0, y0, z0. So this time, your ellipsoid is not based at origin. It's based at this point, x0, y0, z0, but then your coordinate system is here, somewhere else. That doesn't matter. This is your x0, y0, z0, right? This question? Okay, good. Yeah, so this is I mean, if you write this down, for example, if you open these brackets, expand them, you get terms like x squared plus 2x plus 1, things like that, because when you square, we're going to get negative, positive terms like that if you cut any x. It doesn't matter, because eventually you see that this is obtained from the first one by shifting coordinates or shifting the center. So that's same geometric object, same shape. Now, you can say the same thing about all of those cases, actually. Same with, you know, as I said, in all cases, right? So you can have something like this, z minus z0 equal to x minus x0 squared over a squared minus y minus y0 squared over b squared, right? And okay, well, this is also, what kind of shape is this now? Can you tell me? Yes.
A hyperbolic paraboloid?
Again, is a hyperbolic paraboloid, but with center moved to x0, y0, z0. With center moved to another. Exactly. So just if you want to draw this, so this is now x0, y0, z0, and your coordinate here is x, y. But it doesn't matter. It's but I mean, this is not bounded by any chance, right? This goes all the way to infinity in all directions, right? And goes to minus infinity. Down, goes down, and goes up. Another change you can do in these things, and you get essentially the same coordinate, same shape, is what? Can you tell me another kind of manipulation with these equations that essentially doesn't change anything for you? Yes. Sorry?
Can you rotate them?
Yeah, you can rotate them. Yeah, if you rotate by some angle, then you get into more complicated algebraic forms. But you can still, maybe you can at least change x, y, z. You can change x to y, y to z, z. It doesn't matter. It means that you are looking at coordinate system from different perspectives. That's all. Same. You know what I'm saying is that if you see an equation like this, for example, right? I mean, z minus z0 squared over a2 minus x minus x0 squared over b2. This is also a hyperbolic paraboloid. Paraboloid. Right? Except, you know, the role of x, y, z has changed now, but it doesn't matter. So you have to draw here y like this, and your z and x axis are here. Now, which one is z, which one is x, is you have to look at which one corresponds to this exact shape. It doesn't matter. You find the x and z intersection, you find it. That's fine. That's not a problem. Any questions so far? This thing discussed? No? Any questions you might have? No? Okay, good. So there is one kind of surface that's also important, and it doesn't, it's not covered yet by these cases. That's the case where one variable is totally missing from your equation. For example, x is missing, or y is missing, or z is missing. So that's an interesting case. Let me write it down.
Wouldn't we just be moving back to 2D space if that happens?
Yes, but we want to be in 3D space at the same time. So, yeah, indeed, that's the important observation. Yes, but you can look at it in 2D, but then you can also look at the same equation in 3D, and you see that you get something interesting now. Right? So, final case. One of the variables, x or y or z, is missing from the equation. Okay, for example, you can have something like x2 plus y2. Let me just give a simple example, e.g. x2 plus y2 equal to 1. Okay, as it was said, x2 plus y2 equal to 1, you can look at it in R2, in two variables. It's a circle, right? It's of course a circle. But what if I wanted, I want to emphasize that find all x, y, z that satisfy this equation. What kind of shape that would correspond if you look at this equation in 3D space? Okay, many answers. Yes. Sorry.
Never mind.
Okay, it's
Do you get like a cylinder, like a tube?
tube. Yes.
I was gonna say tube.
That's a
All of you are right. Yeah, it's a cylinder, right? Or a tube. Yeah, you like to say tube. Tube also. It's a cylinder. Yeah. So why is it a cylinder? Because I mean, you noticed. I mean, it doesn't matter. You can go at any height. In other words, cut it with any z equal to constant plane. You have exactly the same equation. So you have just this curve, and without any change, you are moving it along the z-axis. So there is this one, and this one. It's a cylinder. Now, the good thing about the cylinder case is that you don't need to consider like even second degree equations. You can consider any equation in x and y and look at it in 3 space. It's going to be a cylinder based on that curve. So in general, any curve in 2D space given by an equation like, okay, so let me just write the equation x2 minus y2 equal to 0. If you look at it in 3D space, gives a cylinder. Gives what we call a cylinder. So, I mean, there is a very important point here, and that this notion of cylinder for us is not just a tube. Is any curve that you take in 2D space. For example, I just had x2 minus y2 equal to 0. I just took that equation. I'm going to look at this equation in 3D space and what kind of shape I get. That's called a cylinder. So if you, for example, look at this, so let me just draw it like that. If you have like a shape like this, right? No question. If you have something like that, if you look at it in 3D space, it's going to be like a wall that's built on this curve in 3D space. So the idea of cylinder is like a curtain. That's a kind of curly curtain. Oops. Anything can go. If you choose any curve on 2D space, you can look at this curve in 3D space, and that's going to be a cylinder. So the idea of cylinder is very general. It's not just a tube. So now let's look at this case, for example. What kind of cylinder this corresponds to? x2 minus y2 equal to 0. What kind of cylinder is it?
Like the one you drew earlier, except make it a cylinder. I don't know how to describe that. Hyperbola.
And you see something curvy, right?
Yeah.
Okay, audience, what kind of, so maybe I should write, so this is the question. What kind of shape in 3D space it represents, this equation? So this is the equation. Okay, as I said, so the analysis goes in two parts. First, we have to understand the curve in the 2D space. What kind of curve is it? Well, you know the curve, right? It's two lines, right? Well, this is x equal to y, x equal to minus y, right? And if you take these two lines, look at these two lines in a space, you're going to get two walls that intersect at z-axis. That's all. So this gives you these two walls now. But these are really straight walls. No curviness here. Right? So these two walls intersect each other. So two intersecting planes. And can you tell me what's the angle of intersection? These two planes intersect at what angle?
90 degrees.
90 degrees. Exactly the angle that these two lines intersect in the plane. So that feature remains when you go to 3D. Okay, so this is a general idea of cylinder. So I think we covered everything in this, the things about quadric surfaces. So going beyond these cases, I mean, there are cases that we didn't cover algebraically, but it needs a little more linear algebra. The linear algebra that's needed, you have learned, I think, in your 1600 course or something. But yeah. You know, have you seen this principal axis theorem in linear algebra? You can change coordinates that any kind of symmetric matrix can be brought into canonical forms. That's part of the canonical form studies. So,
Like matrix transformation?
yeah.
Yes.
You do an orthogonal transformation. That's if you look at the same matrix in that, the new orthogonal system is going to look like exactly one of these shapes that we discussed. So, okay, guys, so thank you so much. You have a wonderful weekend. And assignment 1 is on the way, so it's coming to you very soon. And you didn't have any problem with Gradescope, right? Gradescope is fine. Okay, so let me just stop recording. Stop recording.